Visualizing Quantum Time Evolution using Qiskit in Focused Quantum Tunneling Effect, where team members are Barton Savo, Asha Martinez-Rodriguez, Havish Brahma, Maino Chandram. Our hackathon team was one of the most diverse, with participants ranging in ages from 12 to 20 regardless of their existing knowledge with quantum computing. The hackathon proved to be a valuable learning experience. The most difficult aspect of this hackathon was coming up with a problem statement that was basic enough for a 12-year-old to grasp, yet technical enough for a 20-year-old to implement. In pursuit of a challenge, we went back to the fundamentals of theoretical quantum physics and discovered gold. This project demonstrates how when we're seen from a different angle, even in the most basic notions may provide a challenging problem to tackle. During the process, we were able to read some fantastic community blogs about particle simulations and the usage of quantum computing. We also learned a lot of new things such as split operators, phototransform algorithms, and wave function dynamics while also becoming more comfortable with Qiskit. A quantum mechanical phenomena in which a wave function can propagate across potential barriers known as quantum tunneling. This is one of several possible scenarios in which we can witness the evolution of quantum operators over time. The transmission through a barrier can be finite and is proportional to the height of the width of the barrier. Once set of the barrier, the wave function vanishes and resurfaces on the other. Such a phenomenon is not observed classically, and is limited to only the quantum domain. Quantum tunneling has a lot of exciting applications in a variety of research fields like nuclear fusion, scanning tunneling microscope, quantum computer hardware, tunnel datados, proton decay. Other than that, since electrons can tunnel beyond transistors that are too small, quantum tunneling is expected to put physical constraints on the size of transistors used in microelectronics. That before, simulation of quantum tunneling phenomenon or quantum time evolution in general is a significant problem which if solved could lead to a plethora of industrial use cases. As we discussed before, quantum tunneling is not predicted by the laws of classical mechanics, where surmounting a potential barrier requires potential energy. Thus, this provides us with an exciting opportunity to try and simulate the phenomenon using quantum computers, which inherently uses quantum physics, or solution uses a split operator or a transform algorithm to simulate the quantum tunneling phenomenon in Qiskit. In our proposed solution, we started off with the time evolution wave function of a quantum particle. The Hamiltonian of our system is broken out to split into a finite amount of smaller steps alternating between kinetic and potential propagators using the Light-Schroeder product formula. We initialize the wave function discrete size into two square grid points where n is the number of qubits used in circuit. Following this, we apply the potential operator in the quantum Fourier transform, the kinetic operator, and the inverse QFT. In the desired number of iterations, the circle is then measured and presented as a histogram, which gives us a clear visualization of the quantum tunneling phenomenon. From the algorithm I just described, this is the quantum circle we obtained on Qiskit for 7 number of qubits, where 6 qubits are required for constructing the special grid, and 1 qubit acts as the auxiliary qubit. In future, we have access to more qubits. We could potentially scale our circuit and enhance our solution in more complex model simulation which require more number of qubits. Finally, this is the result we obtained. At the first glance, this may look like any other ordinary histogram, but if you look closely, it actually represents the wave function of a particle tunneling through a barrier qubit 001110 to qubit 00111. After successfully understanding the fundamentals of using a split operator approach to simulate one of particle moving in this project, our new step in the future will be to investigate particle interactions in chemical dynamics, which has tremendous research applications in domains such as drug development, condensed matter physics, and material science. And now I would like to end our presentation with a list of resources we referred during the hackathon. Thank you for watching.